Hello, I'm Aaron Kramer, and this is my legacy project. The problem I have is a very long cylinder of a linear dielectric material is placed in an otherwise uniform electric field E0. Find a resulting field within the cylinder. The radius is A, the susceptibility is chi sub E, and the axis is perpendicular to E0. What you see here right here is, well, this is me mapping out what the given equation is. Well, picture is self-explanatory, and top left hand corner is just basic random notes I know about the problem. My basic equations I got from equation 4.43. It is possible to derive those three equations, but I highly recommend against it because you have to recall material from chapter 2 for boundary conditions 1 and 2. For boundary condition 3, it's a concept in chapter 3, which goes a little bit more in depth. The next section is Laplace's equation. I'll go by this a little bit fast because this is mainly a mathematical concept instead of physics. The equation I used was equation 1.82, and I'm going to pull off a trick. You can ignore the z component. It will make the problem a whole lot easier, and how the problem is stated, you can do that. Right now, you assume that the voltage is a function of S and phi, and since you ignore the z, you don't have the z right there. And after you separate your variables, your equation should look like that equation right there. It might be a little bit nasty, but it really is not that bad. It also is equal to 0. And next, you want to solve for the eigenvalues of the system. Eigenvalues for the S and phi. Eigenvalues for S and phi are those. I decided to chose. And the next thing I want to do is solve for what each function is, the S and my phi. And after you solve for what those two are, they become those two separate entities. And I skipped several steps on purpose because this is mainly a mathematical concept, and I'm using this to mainly use this as an answer manual instead of actual showing you how to do the mathematical steps. That's math, not physics. Next steps I was doing is Fourier series and this basic algebra. I transformed the equations I got in my last slide into a Fourier series from the top. Then from the top to the bottom, this is me doing algebra. I say algebra, well, it's really a combination of Fourier series and algebra. I say algebra because I just simplified them off a little bit more. And I said lambda is equal to 1 and got some initial conditions. Now back to the problem. The equation on the top is to solve Laplace's equation in cylindrical coordinates. The second equation is me using boundary condition 3. Because it's a linear dielectric, I can now apply boundary condition 3 to the Vn also, because also boundary condition 3 says Vn is equal to V out. And right here is also, I'm aware that V out is equal to Vn. I just literally just made them two equal to each other from the last equation, from the last slide. Now when you examine boundary condition number 2, you have that equation right there in the bottom, and you just want to apply those operators on your V out and V in equations, and this is assuming that your radius is the radius of the cylinder. And the top equation is me applying the boundary condition 2 from the last slide, and by careful analysis of my equation, I can tell that Bn and Dn are 0 because if you look at boundary condition 3 does not have a signed term in them. In that case, I just need the n is equal to 1 case because of that. And then the remaining steps are create your basic equations and solve for your constants, which is A1 and C1. And those I got from boundary condition 1 and boundary condition 2. The bottom left is me doing algebra steps, and the bottom right is just me solving for equation number 1 and solving for C1. Next one is just me solving for A1, and then you plug in all those equations back into your Laplace's equation, and you get your potential equation, and then you apply the minus gradient on the potential to get your field.